would like to say thank you to Tech for Impact for this invitation, and of course, all of you for coming. I also have to thank my incredible research team because, you know, I'm the spokesperson, but they really do all of the work. The dog is, of course, not in the lab. He's not on the payroll. He's there for moral support. At any rate, today I have the opportunity to tell you about the world's most porous materials, which we're working on in our lab. Many of you are familiar with sponges, right? Okay, so everybody's seen one of these. We're basically doing the same thing, except the materials that we're making have pores that are about 50,000 times smaller than the diameter of a human hair. Okay, so these materials are extremely porous, and as a result, they can take up loads of different types of guest species. The types of materials that we're working on are known as metal organic frameworks. You're looking at these here. Basically, they're constructed by metals or metal ions that are interlinked by these organic ligands, and these are super special because we can functionalize these organic ligands in ways that we can selectively remove certain species from various gas streams as well as liquid-based streams, okay? So of course, we're interested in a wide variety of separations in my group. Furthermore, the surface areas of these materials are extremely high, so they hold the world record, about 7,800 square meters in a single gram. So what I just had in my hand is approximately 1 gram of material. This is the same surface area as that of a European football field. You notice I didn't say American. So my group is very interested in carbon capture-based applications for these materials. One of the largest point sources for CO2 emissions are power plants. The problem is that carbon dioxide actually is mixed with a load of other small molecules like nitrogen, like water, like oxygen, right? So what we would like to do is design our sponges so that when we stream these gases through the material, we can selectively grab that carbon dioxide, which you're seeing there in the pores of the material. If we design these materials in a special way, so once they're saturated with CO2, right, we could heat those materials up, we could release that, it could be stored underground, or if you design these materials in a special way, you could put reactive sites in here that could activate that CO2, and then you could potentially convert that CO2 into value-added chemicals or fuels, for instance. So because we can grab things selectively from various gas streams, recently we've also moved into water purification, okay? So we've basically taken our sponge. This is a picture of a crystal of our sponge. If you looked on the atomic scale, this is actually what it would look like. We've decorated the inside with polymers, and these polymers have special groups so that they can complex, for instance, heavy metals in solution. So here I'm showing you some data. This is lead, and this is mercury removal, okay? So we start with an initial concentration. We treat it with our sponge. It only removes a little bit of the metal. You notice when we treat it with our sponge that's been decorated with the inside with the polymer, we improve the removal efficiency by factors of 60 and 90 times. And this is super important, not only because we can extract large quantities of these heavy metals, but we can do so at extremely rapid rates, so we can do this in a matter of seconds. So we've tested these materials in a variety of real-world water samples. So we've done wastewater from Swiss industry. We've also done river water and seawater. The reason that we did this was because it's full of organics that foul most adsorbent materials. Furthermore, they've got loads of other metals and things in solution, and we wanted to see how it would alter the efficiency of our materials. So basically what I'm showing you here, we'll just look at the seawater, for instance. Sodium is 14,000 times the concentration of the lead in the seawater. You can see that we can actually selectively extract that lead and leave behind the other metals in solution. So our materials maintain efficiency in a variety of different real-world water samples. This selectivity was extremely exciting to us, and so we decided to look at other metal targets that we might want to remove from liquid streams. We, of course, began looking at precious metals so that we can begin recycling those. As you guys know, a lot of electronic waste is going into the landfills. So we've designed another sponge, shown here. Again, changed the inside, this time to selectively target, for instance, gold. And we've been able to demonstrate that we can actually selectively remove gold from a variety of real-world water samples. You can see all of the different materials here. I'm just showing you one example here. This is a CPU. So what we've done is we've removed the metals, If you look, these metals consist of lots of copper and nickel and a little bit of gold. So we dissolve those metals in solution, we put in our sponge, and we show that our sponge can actually selectively extract that gold and leave behind the copper and nickel. So we're over 600 times more selective for the gold over the copper and nickel. Because we can concentrate a lot of the sponge inside, a lot of the gold inside, then we can basically remove that sponge, okay? And what we're left with is highly pure gold on the back end. It's approximately 23.9 carat, and this is due to the material's very high selectivity. The last SDG that we can have an impact in, we've been working, for instance, in biomass conversion, right? So essentially, we would like to take biomass-derived molecules, and convert those into value-added chemicals and fuels. Recently, one of the postdocs had a really fantastic idea. She said, oh, if we're doing this with natural polymers, then maybe we could do this with synthetic ones. So she's applied for a Tech for Impact grant, and she received a seed grant for 2019 so that she can begin utilizing these materials in order to basically convert plastics into value-added chemicals and fuels. So with that, I'd like to thank you for your attention, and I'll take any questions.